talk about where numbers over finite commutative logarithms.
Obrigado, Petro. Bueno, en primer lugar, quería agradecer a Fabio y a la organización local por invitarme por segunda vez en estos eventos. Estuve en San Carlos previamente y bueno, primera vez en Belo Horizonte, espero esta tarde poder conocer y disfrutar. Y bueno, quería agradecerle a Daniel y el apoyo que ha brindado siempre para hacer estos mismos eventos en Argentina. Siempre estuvo en el comité científico y colaboró un montón para que podamos despegar. Bueno, empezar. Eu não sei falar português. My English is bad y estoy aprendiendo el español. Pero bueno, vamos a intentar hablar.
Detrás. Detrás.
Ese avanza. Okay. Well, this is the plan of the talk. I'm going to do some introduction, then I talk about Waring numbers over finite fields, then we define some graphs over local rings, and we want to compute the Waring number of finite commutative local rings. I'm going to give some explicit formulas, and at the end, we concentrate, we focus on local rings with prime residue fields. Okay. So, a little history first. The classical problem was introduced by Waring. This year, he asked whether given k, the power, there is some natural number such that for every n, one can write this number as S as a sum of S term of k powers. And okay, it is known as the Waring problem. And Hilbert proved that such S always exists. I don't know the proof, but it's using integrals with 25 variables, something crazy. Okay, so we know this as exists, and the minimum S is called the Waring number, okay, and it is denoted GK. So what Hilbert proved is that GK exists for every K, but another problem is to compute it. So these are the first values. Okay. Okay. G1 equal 1 is obvious. G2 equal 4 was given by Lagrange. Same here. And then in the 20th century, these first Waring numbers were computed. You can see here 65, the first mentioned reference to Daniel. I want to remark here that 73 is the only Sheldon prime, Sheldon Cooper from the Big Bang theory. It was proved recently by Thomas and Spicer that this is the thing. 73 is a prime number, which is the 23rd prime number. Its reverse mirror number is 37, which is also prime number. It's the 12th prime number, so the indices are also the reverse one to another. And 3 times 7 is 20. This is a Sheldon prime, and they prove they are the only one. It is the only one. So it's a nice quote. Okay, the famous Lagrange theorem asserts that every natural number is the sum of those 4 squares, so we have this bound. But 3 squares are not enough. For example, for 7 or every number of this form, we cannot use 3 squares. We are forced to use 4 squares. So we have this number. This is easy, but well, the other is more difficult. But we have these numbers. Okay. This is in the integer. Okay. For example, G2 is 4, but we can write for a given number we can use less than the required number of squares. G3 equal 9, but you can use decreasing cubes. Interestingly, and Dixon showed that there are only two integers requiring 9 cubes. But okay, the number is 9. Okay. So in general, we need G4 is 90, but we only need 8 fourths. Okay, the sum of order noted that GK is upper bounded by this expression, and some guys need them like Dixon, and others prove that actually we have equality if we have this condition here. This is the fraction of half effects. However, there are no cases satisfying this, contradicting this condition. So I might also prove that this number must be fine. Later in 1990, Kubina and Wunderlich showed that actually we have this equality for small numbers. For k less than this quantity, and it is conjecture that it holds for every k. Okay, so we have the first values. We compute it using this. We can check the Euler formula holds in these two cases. Okay. Well, so we can think of the Waring number as a problem not in the natural numbers, but also in the integers, in the ring of integers, and one can consider this in the general ring. Okay. So the problem is the same, given the ring and given a positive integer k. One asks if it is possible to express every element of the ring as a sum of s k powers. Now we denote this number, the minimal s. If x is, we don't know, we denote it by grk. I'm interested in Waring number over finite fields and finite commutative rings with identity. In this talk, I will talk over finite commutative local rings. Okay. So for Waring number, let's start with Waring numbers on finite fields first. So if we have a finite field, it is usually denoted, this number is because it comes first. People start studying Waring number with finite field first, and then on the finite rings. So this is a classical notation. This number not always exists. When it exists, we have this reduction here. We can change this k by this smaller k. So we will always assume that k is a divisor of q minus 1. And k is not 1 because if not is 3, we have this here. So for instance, on the finite fields, on the finite field with 16 elements, if we want to compute gk, since the divisor are 1, 3, 5, and 15, we only have to compute these 3 because the other 3 are 1. And these are, of course, normal. I just put in this. So this reduces the problem a lot. Many authors have studied this Waring number, and there are many lower and upper bounds. I don't like bounds too much, so I want exact results. And there are a few exact results. For instance, this is using book theory or sheet. We have these extreme values are known first two, the last one, and the half. They are equal to K. G1 is 1, G2 is 2, P minus 1 is P minus 1. So, there are results of Cipher and Cochrane. If you have this slide is for P prime. Okay? If P can be written in a combination of squares of two integers, we have these strange formulas. Okay, this and this one. And for example, this is a result of small study. A small study. This problem in set M, integers modulo M. You see, GK is 2 if K is sufficiently small. GK is small for K, sufficiently small. Then we have this result of Moreno-Castro. G is also 2 for K dividing this power of P plus 1. And we have solved the remaining case here with Denis Videla. This is joint work with Denis Videla. Denis was a former student of mine. This is an interesting result of Winterhoff and Van der Waals-Tigne. They proved this for M1. Then Conan generalized this result, but the difficult case is truly is M1. And well, you have here 2 primes, P, R primes, as that P is a primitive root model of R to the M. Here the phi function, the other phi function. And if the 2 primes are off, we have a better result. Okay, and these are all the exact results that I know. This is for P to the M. Okay. We have studied these numbers using Cayley graphs. Some Cayley graph known as generalization of the classical Cayley graph. Okay. What is a Cayley graph? If you take any abelian group and subset S not containing 0, you take the graph whose vertex is the group, and two vertex are form an edge if they differ. If the difference is in S. S is called the connections. Okay. So this graph has no loops because with 0 is S regular, and it's undirected if the connection set is symmetric. For instance, if you have a subgroup. But in general here, you take two vertices. If you have an arc, in principle, these graphs are oriented. They have arcs. But if S is symmetric, I really have 2 arcs. I don't want this, and it's typical in the theory to, in this situation, we consider as an undirected edge, okay, in this sense. So the general Cayley graph is the Cayley graph whose vertex set is the finite field, and the connection set is the set of K powers. Okay. So 2 vertices form an edge. If they define in a K power, is n regular, where this is the degree of regularity, the principal eigenvalue. And it is undirected if and only if satisfies the condition. Either P is even or P is odd and K divides this number. Okay. So we have the result. I say that the one number not always exits, but when it exits, it is equivalent that this graph is correct. Okay. Or arithmetically, it is the same to say that the degree of regularity is a primitive divisor which is the same to say that M is the order of the module F. The list. This is integer. Let's find this. Well, so what is the relation? The diameter of a graph is the greatest length between all the minimal length. Okay, this is denoted delta. So you see here. If I have a vertex, I sum power, key power, and I have an edge, and then I can go adding another key power. Eventually, I can have cycles. But if not, at least I have a walk. So there is a walk from U to B of length F, if and only if there is elements in the field, not zero, such that we have this. And this looks like what I'm looking for, the bottom line. So if the graph is connected, then running number exists, but it's given by the diameter of the graph. This is interesting. And we studied this in these two works with Denis. This is the third one, and this is here we study a reduction form. Okay. Now we want to study this number on a finite commutative local ring. Okay. So it's a ring with a unique maximal area through the diameter of similar graphs related to the ring and K power. And for now on, we assume this K is co-prime with the size of the ring. Since I'm considering here a local ring, this is not a cubic restriction because this is power of 1. Okay. So I'm considering most of cases. Okay. So the graph, sorry. We have a R, a fast ring, commutative ring with identity. We define these graphs, same. The vertex set is the ring, and the connection sets are the K power. The only difference here we take the units, and here we take the non-zero. So in the second case, we can have important elements. So eventually we can have loops, some loops. Okay. For instance, well, if K is 1, we have the classical unitary K graphs. When I form an edge between if U and B differ by unit, okay? And we have this obvious impression. The graph, this graph is undirected, if and only if this is undirected. And we have this condition similar for finite fields, arithmetical conditions. This is an if and only if, but if this is connected, this one is connected. As I said before, this graph may have loops. I will need both graphs. I wanted to define only one, but we need this one. Okay. So what is the structure of the graphs for local ring? First, we study the cosets. So we have under this general hypothesis, a finite commutative local ring with identity, and we take K co-prime with the size. Then we have these are technical results. Taking X to X in K is a bijection of the cosets. But the important thing here is, in terms of vertices and arcs, we have, if I have an edge, suppose we have a vertex A and the coset, and a vertex B and the coset. So if I have an edge from A to B, every vertex here is connected to every vertex. I have particle be complete. Complete different. Okay. So the result, this is very important because this gives the structure of the graph. The graph, here K, can be seen is a balanced blow-up of order M, or it is this parameter product. Here I have the graph associated to the ring, and here I have the graph associated to the residue field. Okay, and this is the complete KM. M is the size of the ideal. This little circle is mean that we have to add a loop in every vertex, so that the chronicle product is the explosion balance flow. What is this? For instance, if you have C4, what is the balance flow up of order 3, you replace each vertex by a set of 3 independent vertices, and each edge by the complete bipartite. Okay. So they have a lot of symmetry, this rest of the vertex. Okay. Well, the chronicle product is of graphs is just take the vertex sets of the product is the product, the Cartesian product of the vertices. Two vertices here form an edge if each coordinate form an edge in each graph. Okay. So, for instance, if you take this local ring, set BR, this is a maximal idea, and we have this decomposition. The graph of the K power in set PR is the chronicle product of the graph of the K power in set P multiplied by this complete. So we want to compute the Waring number, and we want to relate it to the diameter of the graph. So the first result is the following: if these graphs are connected with finite diameter, then the Waring number exists and is given the diameter of the graph. The same for this one. If it is connected with finite diameter, then it is then this is also connected. The Waring number exists, and we have this relation. You see, the Waring number is given by the diameter of this graph, and we have this one. But we have a good decomposition for this one. So I want this to be an inequality. Okay, this holds for every error, not only local, not only a local one, but for local ring, I will have equality here. Okay, This is something technical because I have always to divide directed and undirected case. The directed case, I will need the girth. The girth is the minimal length, the length of the minimal cycle. Okay. So if the girth of the graph is greater than the diameter, it only differs by one. It cannot be too much longer. So, since we have seen these two previous results, the varying number is given in terms of the diameters. I have equality here, but not here, and I know the structure of this graph. I want to compute the diameter of chromatic products, okay, and then try to push, to have equality. So we have studied the diameter of this kind of product of graphs. Basically, you see, unless trivial cases, for instance, in the undirected case, if gamma is not a complete graph, is the diameter of the graph is the diameter of this one. I can forget about this part. And in the directed case, diameter is given by the diameter of gamma or the diameter of gamma plus 1, depending on whether the girth is less than or equal or greater than the diameter of the graph. This is something technical, but that's what we have. Okay. So I want to give the general result, but first I have to, since I'm looking for the diameter, I study first the distance between vertices, and we have the following. For any finite commutative local ring, residue field of K of prime characteristic, and K for prime with P. And suppose this arithmetic condition is to ensure that numbers exist. The distance of A and B in this graph is less than or equal to the distance of these two vertices in this another. And the equality holds if B is not the same coset. Again, separating the cases when the graph here is directed or undirected, we have that the distance between two vertices in the same coset is 2. This is because you can see here these are independent, but I have a common graph here, so the distance. There's that. Okay. And in the directed case, the distance is given by the girth of the graph. Okay. So we can give the main result, let's say, which is how much is the varying number GRK for our the commutative local group. So if we have this arithmetic condition here again, K is coprime with Q, and define K prime is with the common. If this is a primitive divisor of Q minus 1, then the varying number over the ring exists. This graph is connected, and here we have equality. We already have this, but now we have this equality. This is important. Moreover, using the previous result, this can compute using the structure of this graph, GRK, that GRK is basically, and let's do the cases, GKQ, the varying number over final field. Which final field? The final field, FQ, is the residue field. FQ. And something similar for the directed case. In this case, this varying number of the ring is the varying number of the final field, the residue final field, or the same varying number plus 1. Okay? So I like this result very much because we completely reduce the computation of varying number of final commutative local rings to the computation of varying number of final fields. And these are better understood. There are a lot of information. So it's, I'm more precisely to compute this varying number, it is enough to compute this. Okay. And also, if you take any pair of commutative local rings having the same up to isomorphism residue field, the varying number will be the same. Okay, this is the general result. So I want to say some word about the error reduction formula. In a paper of Winterhoff in 1988, he gave the following reduction bound in the case of a prime field. Okay, if this varying number exists, this varying number is less than or equal to n times this varying number over the prime field. This is interesting. We reduce a lot the computation. M could be very big. This D here had to satisfy this, had to be of the form. It's a divisor of K that can be written in this way or this way. Okay, something very concrete. Built-in, I want to translate this in the way I write. So built-in M, right in fixing this notation, this can be written in this way. It is the same formula, but now I'm changing the role of K. Okay. So this is the result of WIG. We want to reduce varying numbers over a final field FQ to a subfield, the varying number of subfield, not necessarily prime field. So with Denis in this work, I told you before, we get the following reduction formula. If we have the order of C, if A is the order of C modulo of B, and A is the order of BC modulo P, then this varying number exists, and we have this exact reduction formula for varying numbers. Okay? From this field to this field, small field. Well, if you want to compare our reduction formula with the reduction bound, they are very different. They look similar, but if you want them to coincide, they can only be A equal 1, B equal N. Okay? You want this, equal this, and they are generically very different. So we get a new result there. I also like this result because it's a reduction formula for a number that is difficult to This was for final field. Now we can do the same for rings, for local rings. From now on, let's denote R sub A any finite commutative local ring with identity whose residue field have size B to the A. Because I know it is enough, I only have to look at the size. So if we have again a B prime and ABC satisfying these arithmetic conditions, these numbers exit, and we have reduction formulas. But now I have to distinguish again the directed and the undirected case. In the undirected case, which is this is the condition to have undirected graph. Either P is even or P is odd and P is even. We have this again, this reduction formula. See, this is a bigger ring than this one. And in the directed case, again, we have, in one case, the exact reduction formula, and in the other case, we have to pay the price here, -1, because we have a difference in the formula. This difference here, I have to arrange the formula, but I still have this varying number is B times a varying number -1. Okay. So this is for reduction. Now explicit formulas. Again, I mentioned the exact formula for Winterhoff ornament. So we can give the same formula for rings using all the theorems before. So this formula of Winterhoff and Cononen still holds for every local ring. Okay, whose residue field is of this size. The formulas are the same, but here you can take any finite point. Well, using these explicit results and the reduction formula, for instance, we can give this kind of formulas, you know. For instance, here, if this is trivial, if this is 1, I have that this number equal B. So when this equal 1, studying these things, I come to this kind of expression, this varying number equal B. And this kind, well, of course, I have this number here, I need that B divides this number. When this happens, this is not an if and only, but almost. This kind of formula happens if I have several possibilities. The easiest one is that you have a prime different from P, such that P to the A equal 1 R. If you have this, you have this. This is just write this in the form. Okay. A lot of another possibilities. So, using, for instance, only this first condition here, this formula, this general formula holds, and we can produce examples. For instance, this is a command in the framework. Equal to, yeah. That's a broken access. And this is equal to. And then you can play with B and A, and you have a bunch of numbers. What happened with B equal 3. I have this. This is clear, but this seems strange because. Sorry. I want to take B equal 3 here. This is clearly this holds for P. I need P to the common to 1 of R is 3. Okay? See, P equal so this one, if P is common to 1, A can be anything. But if P equals is common to 2, I have to take A over even. Okay. So I have this 4 and this 6 here. I'm playing with this, you get all this. Just with the third condition here. But you can play with even 2 times R or the product of 2 prime. Okay. I don't want to play too much. Okay. So to finish, we focus on local rings having the maximum ideal of the biggest size. Okay. So about the residue field is the prime field. Okay. Now we consider a local ring R with a maximal ideal of this size. This is just remember. We have an arithmetic condition in the theorem, and it's automatic here. The condition was that this number is a primitive divisor of the number, but if this is prime, it's automatic because I have no powers. So the right number always exists in these cases. And okay, I have to distinguish P equal to. Consider a local ring of size P to the S, having residue prime field FP. So this right number always exists for P equal to 2, trivial. And in the case P is solved, we distinguish the directed and undirected case. And again, you have basically same results, but this number always exists. And again, I can give some extra values here. For instance, the right number in the extreme cases. G2, G minus 1, G minus 1 or 2. And in case S is equal to 2, local rings of over P squared, we can give this extra value. P plus 1 over 2 is equal to 2 when R is a field, and equal to 2 or 3 when it's not a field. These are the only possibilities. There are only 3 up to isomorphism of local rings of square. These are general results, and well, you can play, for instance, let's do an example. Take P5 square 25, and let's take the rings, not the field. We have only these 2 rings. And by the previous corollaries, we have that G2, G3, and 2. P is 5, so I am in this case 5 equal to 1, E2 is 2, is the same, G4 is 5, and I am in this case, and in this case, G3 is 2. So we get these values, and we can check. We have here all the squares, the cubes, and 4 powers. Well, okay. Take a moment. You have 1 minute. Okay. From this, it is clear that every element can be written as a sum of 2 squares, 2 cubes, and 5 fourth powers. But not all the elements are a square or a cube, okay? Or can be written as sums of less than 5 fourth powers. For instance, we have these expressions: 2 squared, 2 cubes, and 5 fourth powers. You can see here better. 1 plus 14, 1 plus 14, 1 plus 1, 11, 1. But there are all a lot of possibilities. I don't know the only one. But there are, at least you have these sums. Okay. Well, I said this. This is a work with Denis Videla. Some final remarks.
5 minutes.
Okay. It's actually answers to questions in the sense. Because you ask question in order. So no, that you don't know how to attack this case. Okay. Yes. And yes, we know how to do this in the general case, not for the local ring, but in the general case. This is a work in progress. Well, this is easy to living up. Yes. Yes.
Yes.
We use the art in the composition. If R is not local, it is not a local ring. Okay, here we have to use another product, but this one is the strong product, has this strong product decomposition of small graphs. And basically we get the running number is the diameter of the graph, but the diameter of the strong product is not the product or the sum of the diameter, but the maximum. So we get this kind of, and this reduces again all to final fits. But we don't have, I don't have much detail than that. This is a work in progress. Okay.
Thank you very much.
Oh, sorry. I missed it down. No. Yes.
Is there any more?
No. No, but the last one is just propaganda. Just to invite you to come to Argentina. The next the final field. Yes, it's already in November, December, but this time in Buenos Aires.
And days?
No, it is not,
Are we not?
because we are just organizing.
Yeah. Okay.
But-
So
Yeah, I didn't tell you.
Vocês veem para o patrocinante em julho e fica até dezembro para o patrocinante da Argentina.
Okay.
Eu já ouvi.
So, thank you very much for the very next talk. Are there any, does anybody other than Daniel have questions?
My son.
No, it's, No, I'm just joking. I think Daniel has a question.
It's already easier, right?
The addition or some part of the addition. So you said that in over finite case, there are fields that that does not exist as one. It's totally characterized which of those fields is totally known, or there are only
No, just the arithmetic condition, but I don't know. Yes, structural.
Yeah. But there is some issue
We
that,
have this. Yes, I don't know. I think no.
yeah,
We have only this arithmetic condition, but you are asking which are the fields that
that's right.
I don't know.
Yeah, you can check it, but
No, but I think I never saw a paper studying this.
Yeah.
And you can do it. Okay.
that's no question.
Any more questions or remarks? So just out of curiosity, have you looked in some possible applications or?
No, I don't know applications. I know. Maybe I don't know. The answer is I don't know, but maybe in some algorithm or probably some cryptography trying to use a small quantity of squares or a lot. I don't know. I never heard of applications.
The paper of Arne doesn't have any comments on applications. I
don't remember.
You are thinking of something.
No, because it's
Yeah, probably.
But I don't.
but it's probably that there are some kind of applications. But the question is not difficult.
It's very interesting that you managed to get with graph theory, with a lot of graph theory, answering this question.
Yes, because
very
it's, for instance, yes, if you pick the right graph, for instance, you can take graph and the connection set can be the units or the nilpotents, or you see it. So the structure of the wheel, you say the structure in a graph.
I think it's over to the
Yes.
More questions or not? So if not, let's thank you.